Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, that have shown impressive abilities in understanding and generating language, as well as in complex reasoning through their chain of thought capabilities. We build on this by exploring multimodal large language models, MLLMs, which integrate visual information to handle a wider range of tasks, including visual spatial reasoning and navigation. However, we note that these models still rely on text-based reasoning during inference, which may not be the best approach for tasks that are heavily visual or designed to be vision first. Evidence from recent multimodal benchmarks suggests that reasoning based solely on language can be inadequate, especially in areas involving spatial or physical dynamics. This reliance on converting visual information into text creates a gap that limits the model's ability to effectively utilize visual features. For example, tasks like navigating a maze or designing a room are often better approached with visual representations rather than verbal descriptions, which can miss complex spatial relationships. This leads us to a key question: can models plan using non-verbal modalities, like images, without relying on text? Cognitive science supports this inquiry, as dual coding theory indicates that human cognition uses both verbal and nonverbal channels independently. While some recent MLLMs have started to incorporate both text and images in their reasoning, they still fundamentally depend on text, using visual aids as secondary support. To address this gap, we propose a new approach called visual planning, where reasoning is conducted entirely through images without any text involvement. This is, to our knowledge, the first attempt to see if models can plan using only visual representations. Instead of generating text-based rationales, our method creates visualizations that represent planning steps directly in images. This approach avoids the issues that arise when visual tasks are forced into verbal explanations and enhances the tracking of state transitions for tasks like navigation and visual problem solving. We explore this paradigm using a large vision model, LVM, trained solely on images and videos, eliminating the influence of textual data. This allows us to investigate whether models can reason purely within the visual domain. Inspired by the success of reinforcement learning, RL, in language reasoning, we introduce visual planning via reinforcement learning, VPRL, a two-stage RL framework designed for visual planning. This framework includes an initial stage that encourages exploration, followed by reinforcement learning with a reward function based on progress. We test our approach on grid-based navigation tasks, such as maze, frozen lake, and MINIBEHAVIOR, where an agent must navigate to a target without breaking environmental rules. Our results show that the visual planning paradigm significantly outperforms traditional text-based reasoning methods, achieving over 40% higher average exact match rates. Additionally, VPRL demonstrates better generalization to new scenarios compared to supervised fine-tuning methods. Our contributions include the introduction of the visual planning paradigm, the VPRL framework, and empirical evidence that VPRL outperforms traditional methods in visual spatial planning tasks, leading to improved performance and generalization. Section Summary. In this section, we introduce a new reasoning paradigm called visual planning, which enables models to perform planning purely through visual representations without relying on text. We also present VPRL, a two-stage reinforcement learning framework that significantly outperforms traditional text-based reasoning methods in visual spatial planning tasks, demonstrating improved performance and generalization. Section: Visual Planning via Reinforcement Learning. In this section, we discuss our approach to visual planning through reinforcement learning. Most previous benchmarks in visual reasoning typically involve translating visual information into text and then performing reasoning based on that text. This means that once we convert visual content into text, the task becomes a language reasoning problem, where the visual information isn't utilized during reasoning. Our visual planning approach is different. We focus on planning directly within the visual domain. We define visual planning as the process of creating a series of intermediate images, where each image represents a visual state that together forms a visual planning trajectory, starting from an initial input image. We denote our generative vision model as pi_theta. Reinforcement learning, RL, has proven effective in enhancing the generalization of autoregressive models by using rewards based on entire sequences rather than just individual tokens. In our visual planning framework, we adopt an RL-based training method supported by Group Relative Policy Optimization, GRPO. This method uses transitions between visual states to calculate rewards while ensuring that we meet environmental constraints. To encourage our policy model to generate valid actions and explore diverse options during the RL process, we introduce a two-stage framework. In Stage 1, we initialize the policy model by training it on random trajectories created through random walks in a simulated environment. Here, we aim to produce valid sequences of visual states while maintaining exploration capabilities. Each trajectory consists of a series of visual states, and we extract pairs of images to train the model on plausible next states. Stage 2 builds on the initialization from Stage 1, where the model has developed effective exploration skills. This stage allows the model to simulate potential actions by generating the next visual state and guiding the planning process. The RL algorithm provides feedback and rewards based on the accuracy of these simulated actions, helping the model learn effective visual planning. In this stage, the behavior model samples a group of candidate responses, each representing a possible visual state linked to a planned action. We use a rule-based function to interpret these transitions and score them with a reward function that measures progress toward the goal. Instead of relying on a complex learned critic, GRPO offers a more efficient way to compute training signals by comparing relative advantages among candidates. For our reward design, we focus on whether the generated visual state accurately reflects the intended planning action. We define a function to interpret the intended action connecting the current state to the generated candidate state. We also introduce a progress map to estimate the effort needed to reach the goal from each visual state. By comparing the current and resulting states against this map, we categorize actions into valid and invalid transitions. Finally, we propose a progress reward function that assigns rewards based on whether actions lead to progress, do not progress, or are invalid. In our experiments, we set specific reward coefficients to encourage progress, assign no reward for non-progressing actions, and impose penalties for invalid transitions. Section Summary. In this section, we introduce a novel visual planning paradigm that generates sequences of intermediate images purely within the visual modality, contrasting with traditional methods that rely on textual reasoning. We detail a two-stage reinforcement learning framework that first initializes a policy model through supervised learning on random trajectories and then optimizes it using reinforcement learning to enhance exploration and effective visual planning, with a focus on designing rewards that encourage meaningful progress toward goals while adhering to environmental constraints. Section: System Variants. In this section, we present various training system variants alongside VPRL as baselines, differing in supervision types, language versus image, and optimization methods, supervised fine-tuning versus reinforcement learning. This allows us to compare language-based and vision-based planning while evaluating the impact of reinforcement learning. We introduce visual planning via fine-tuning, VPFT, as a simpler version of our framework. It uses the same training setup as Stage 1 but replaces random paths with optimal planning paths. For each environment, we select a specific trajectory that represents the shortest route from the starting point to the goal. The model learns to predict the next state based on the previous states, with the goal being the same as in our earlier equations, guided by the optimal trajectory. In the supervised fine-tuning, SFT, baseline, we focus on planning through language. Instead of creating a visual representation of actions, the model generates a text description of the action sequence. Given a visual input and a task description, the model is trained to produce a sequence of actions in text form. To test our visual planning approach, we choose tasks that can be fully expressed and executed visually. We focus on tasks where we can observe state changes visually, unlike language-based tasks such as code generation. This setup allows us to analyze planning behavior without relying on text explanations. We conduct experiments in 3 visual navigation environments: FROZENLAKE, maze, and MINIBEHAVIOR, all solvable through both visual and language-based methods, enabling a direct comparison. FROZENLAKE simulates a grid where the agent must navigate from a starting position to a destination without falling into holes. In maze, the model must navigate through a maze from a starting point to a destination based on an initial image. MINIBEHAVIOR requires the agent to pick up a printer and drop it at a table, involving additional actions like picking and dropping. We create synthetic datasets for these tasks with varying complexities, and further details are available in the appendix. To investigate visual planning without language interference, we use models trained solely on visual data. For our methods, VPFT and VPRL, we utilize the Large Vision Model, LVM3B, which is trained only on images and videos. We also provide details on the rule-based state action parsing function and progress map in the appendix. Additionally, we include textual planning baselines for comparison, evaluating models like Qwen 2.5-VL Instruct and closed-source models such as Gemini 2.0 Flash and Gemini 2.5 Pro. For evaluation, we use 2 metrics: exact match, M, which checks if the model generates the correct planning trajectory, and progress rate, PR, which measures the ratio of correct steps taken towards the optimal path. This gives us insight into the model's ability to make meaningful progress. Our results show that visual planners, VPFT and VPRL, outperform all language-based reasoning models across all tasks. VPFT, using the same training method, surpasses language-based SFT by over 22% in M, with VPRL achieving even better results. This demonstrates the effectiveness of visual planning in tasks where language approaches may not align well with the task structure. Inference-only models struggle with these tasks, with even advanced models like Gemini 2.5 Pro performing poorly on complex tasks. The 2-stage reinforcement learning approach, VPRL, achieves the best overall performance, significantly improving upon the supervised baseline VPFT. After stage 2, the model performs nearly perfectly on the simpler FROZENLAKE task and maintains strong results on maze and MINIBEHAVIOR, showing over a 20% improvement across all tasks. The first stage of RL training, which focuses on output format without teaching planning, results in random performance. However, after full optimization in stage 2, the planner excels, highlighting the advantages of RL over SFT. We also find that the benefits of RL persist as we increase task difficulty. As the grid size in FROZENLAKE grows, the performance of other models declines sharply, while our visual planners maintain higher accuracy and stability. VPRL shows even greater robustness, achieving strong results across different grid sizes. We observe similar trends in other tasks, with more details available in the appendix. Section Summary. In this section, we present various training system variants for visual planning, including visual planning via fine-tuning, VPFT, and reinforcement learning, VPRL, to compare language-based and vision-based approaches. Our experiments demonstrate that visual planners outperform language reasoning models across multiple tasks, with VPRL achieving the highest performance, particularly in more complex environments, highlighting the advantages of reinforcement learning in planning tasks. Section: Discussions and Analysis. In this section, we discuss our findings and analysis, focusing on error analysis and a case study. We present visual planning traces generated by our model, LVM, across various tasks. As we noted earlier, the model sometimes makes non-optimal choices that stray from the shortest path, as illustrated in the FROZENLAKE example. Invalid actions can include breaking physical rules, like walking through walls in maze or entering the table in MINIBEHAVIOR, or performing multiple actions at once. We compare visual planning with language-based reasoning systems. In FROZENLAKE, we observed that Gemini 2.5 Pro misjudges the environment size at the first step, leading to a series of errors and an incorrect final answer. Similarly, the language-based SFT baseline makes an invalid move at the third step, showing challenges in tracking states during reasoning. In contrast, our visual planning approach avoids these mistakes by reasoning directly with visual information and updating visual states with each action. We find that VPRL can take detours to navigate around obstacles while still moving toward the goal, whereas VPFT lacks this adaptability and often gets stuck. We provide more examples in the appendix. Next, we explore whether we could use VPFT directly as the policy model for GRPO training instead of starting with random trajectories. We believe that VPFT, trained with teacher forcing, limits exploration by consistently producing similar actions, which leads to the same rewards. This results in no advantage, preventing policy updates and effective learning. Our experiments confirm this, showing that VPFT's exploration capabilities decline rapidly during training, nearing zero entropy, indicating significant exploration constraints. Although earlier VPFT checkpoints show higher entropy, they also result in many invalid actions. In contrast, VPRL Stage 1 maintains much higher entropy, similar to a uniform random planner, while having a lower rate of invalid actions. These findings highlight the importance of random initialization in our reinforcement learning framework for effective exploration. Another key advantage of VPRL is its ability to reduce invalid actions. We analyze failed trajectories and calculate the proportion that includes at least one invalid action, which we call the invalid failure ratio. Our results show that VPFT has a high ratio, ranging from 61% to 78% across 3 tasks, while VPRL reduces this ratio by at least 24% in all cases. This indicates that VPRL not only enhances success rates but also helps the model remain within valid action spaces during planning. We also discuss recent advancements in MLLM reasoning, where methods have integrated visual inputs into symbolic forms like graphs or bounding boxes. Some approaches use tools for visualizations during reasoning, such as the O3 model, which employs visual rationales through cropping and zooming. MVOT also generates visualizations of textual reasoning without relying on external modules. However, these methods primarily reason in language, using visuals only to support the text. In our work, we take a step further by investigating whether multi-step planning can occur solely within visual representations, allowing reasoning without any language dependence. Finally, we note that reinforcement learning has been applied to various vision-related tasks, particularly with the emergence of GRPO in DeepSeek R1. In object detection, visual perception is enhanced by rewarding high intersection over union scores between predicted and actual bounding boxes. For visual reasoning tasks like visual question answering, GRPO has been used to improve models for longer and more coherent reasoning in textual responses. Recently, similar methods have been applied to image generation, guiding models to refine images based on textual instructions. While these approaches focus on pixel-level accuracy and semantic alignment with text, our work utilizes reinforcement learning for goal-oriented visual planning, optimizing decision-making through visual state transitions without relying on language. Our visual planning paradigm and 2-stage training framework, VPRL, enable more natural and flexible policy exploration entirely in the visual domain, outperforming all language-based training methods.